Hello friends, and welcome to CNN Cleaning's Cleaning Chemical class. One of the things we often talk about and rarely understand as cleaners is pH. Sure, we know to use this pH on this and that pH on that, but few know why and the science behind why it even matters. So today we're going to take a few minutes to look into exactly what pH is. On to the chemistry. In many of our videos, we talk a lot about hydrogen and oxygen, two very important elements, not just in cleaning, but everywhere. We went over what makes oxygen so special in the oxidizers video, so go watch that. Seriously. Oh, you're still here? Okay, well here's a brief review. Oxygen has 2 less electrons in its outer valence shell than it wants, so it tries its best to fill that hole, to the point where you will never see a naturally occurring neutrally charged oxygen. Oxygen will beg, borrow, steal, or sleep around with others in order to fill that hole it has in its heart. Once it fills that hole, oxygen will have a -2 charge on its own, with 2 more electrons than protons. And then there's hydrogen. Hydrogen is also pretty cool as far as elements go. Hydrogen is numero uno on the periodic table. It is the absolute basicest of elements, the basis for everything else. 1 proton, 1 electron. This electron poses a problem, because in that valence shell, the first one, hydrogen really wants 2 or none. 1 by itself is an issue in the same way that 6 is an issue for oxygen. And that's why you'll never see a hydrogen atom with a neutral charge occurring naturally. They'll always pop up with a +1 charge, since it's easier to just pass that electron off and do without. So what does this have to do with pH? Well, because oxygen is pretty much always negative, having 2 extra electrons, and hydrogen is always positive, having no electrons at all, they readily join together with a covalent bond to form OH-, oxygen and a -2 charge, hydrogen and a +1 charge. So by sharing electrons, they bond with an overall -1 charge as the molecule hydroxide. At this point, we should understand the 2 parts that make a pH, hydroxide and hydrogen ions, and how they can exist in a natural state. And if you look at those 2 together, you'll probably notice a similarity to another molecule we talk about a lot, water. But let's pause on that. Before we go much further, I think we should talk just 20 seconds about probabilities and statistics in chemistry. No need to pull out a calculator or anything. No math is going to happen here yet. Nothing in the natural world is ever absolute, and it's critical to remember that when you're talking about molecules and atoms and their interactions. If you were to take an amount of water, H2O, there is a high probability that each molecule is going to be bonded in the familiar HOH format. But there is some statistical population of molecules that are going to exist as hydrogen ions and as hydroxide molecules. You could say that if you just reach in and pull out a chunk of molecule from water, there's a high probability it would be an H2O molecule. There's a low probability that it would be either hydroxide or hydrogen, and the probabilities it is either one of those is the same. In a pure water environment, the population of both hydroxide and hydrogen is going to be very low, and their numbers will be equal. But that relationship changes when we begin to add stuff to the water. As other molecules are added, some of that water moves around, bonds to other stuff. There begins to be a change in the balance of hydroxide to hydrogen. That balance, that count of excess hydroxide or hydrogen atoms, is the definition of pH, which is an acronym for potential hydrogen, the measure of hydrogen available to bond to other stuff, the hydrogen that is not in the form of water. Water, with a balance of hydroxide and hydrogen, has a pH of 7 on the logarithmic scale of 0 to 14, which we call the pH scale. If there are more hydroxide molecules, the scale progresses to the right, more than 7, and the solution is described as being alkaline or basic. If there are more hydrogen ions than hydroxide molecules, the scale progresses to the left, less than 7, and the solution is described as being acidic. The scale is logarithmic, so as the scale moves from 5 to 4, for example, it has 10 times more hydrogen ions available. Moving from 5 to 3 means there's 100 times more available hydrogen ions, and so forth. Same on the other side of the scale for hydroxide molecules. One interesting tidbit of the pH scale, it is probably more accurate to call it the pOH scale, since the amount of hydroxide increases, the number on the scale increases. The scale is actually the inverse of the potential hydrogen, but hey, that's not my battle. There are also solutions that exist on the outside edges of the scale. For example, acids with a pH lower than 1 and alkalines with a pH greater than 14. But for the most part, the cleaning chemicals we are going to be using are going to exist somewhere between a pH of 2 and a pH of 13, which is still quite the range. We'll continue this discussion in the next video, where we can talk about which chemicals fall where on the scale and what that means for their use. So join us for part 2 of the pH series. Thanks for watching.